plus the bonds. You can also think of it as the valence electrons minus the dots plus lines. For instance, if I was going to do the one for carbon, I know carbon's, oh, well, you could do it that way too. So half of the electrons in bonds is equal to the number of bonds. For example, let's take a look at these two right here. So there are 4 electrons in there, and half of 4 is 2, or you could just say there are 2 bonds. All right. Yeah, I'm not really surprised. It could make it easier, but no. Why would our book make it easier? That would be just crazy. Okay, so for example, carbon has 4 valence electrons. So we say 4, and then this would be 3, 2, 1, 0. The formal charge on carbon is 0. And then with oxygen, we'll do oxygen in purple. Oxygen's is 6, so 6, 5, 4, 3, 2, 1, 0. So that's 0. And since the other one's identical to the oxygen we just calculated, that's also 0. Okay. So you can do the formula. This is probably a little easier than the formula. Just remember, you add the dots and you add the lines, and you take the valence electrons and just subtract them from there. All right. Anybody need a second on this page? Everybody good? All right. Okay. So let's see. I think of well, no, that wouldn't make any sense. Hang on, I'm trying to think of like some examples of a couple of different structures we could do, but yeah, like I can't think of any. So let me look in your textbook for a second. I'll look at the end of the chapter. Really? I didn't actually sign out. Sorry, it's telling me I signed out of the book, which I didn't. All right, so we're going to go with chapter 4, end of chapter 4, go to the summary. See, on our homework this week, there's an NH4. So is it like this? Let's see. Or do you mean that there's this one and this one? They're separate. Okay, so they're different questions. How challenging. I think compared to the last test, as long as you prepare well, this one should feel easier because there's less material on it. It asks about the formal charge on each atom. Okay, so we'll go over that. Might as well do that now because that's 2 really good examples. All right, so let me start. We'll do NH4 first. So we have NH4 plus. So we're going to add all of the valence electrons together. So nitrogen is 5, hydrogen is 1, and we have 4 hydrogen. And then we also have the positive charge. So that means we're going to remove 1. So basically that's like -1. So it'd be 5 plus 4 is 9. 9 minus 1 is 8. So if the charge is positive, you remove an electron. If the charge is negative, you add electrons to it. All right, so what's the next step? What do I determine now? Yeah, draw the structure. Yep, so central atom. All right, so can hydrogen be the central atom? No, never, never, never. It's always on the outside. Correct. Nitrogen's in the middle, surrounded by 4 hydrogen. All right. So, and then how many have we used? We've used 8. So we don't need any more. Now we check to see if there's an octet. Hydrogen is always outside. That is correct. So does nitrogen have an octet? Yes. Correct. The octets and the duets are satisfied. The duets are for hydrogen, and the octet is the nitrogen. Is an essential atom the one with the least amount of electrons? Actually, no. It's the one that's least electronegative. So electronegative just means how much is it going to pull the electrons toward it, but it doesn't mean it has less electrons. It just means it's less likely to pull the electrons toward it. So if I had, let's see, FO4 or something like that, well, that wouldn't even work. Let's see. Gosh, we'll do XeF3. All right. So fluorine is the most electronegative thing on the periodic table. So the one that's less electronegative is xenon. But we all know that xenon has 8 electrons, but is less electronegative. All it means is it's got less of a negative charge. All right. So let's take a look at nitrogen. Nitrogen has, you're welcome, nitrogen has a valence of 5. So if nitrogen's valence is 5, be 5, 4, 3, 2, 1. So it's going to be plus 1. And hydrogen, and of course for the structure, don't forget the brackets and the charge. And for the hydrogen, hydrogen has 1 valence electron, so that's 1 minus its 1 bond, so that's 0. Right. And we want to add up all the charges and make sure they equal to plus 1. So it's 0 plus 0 plus 0 plus 0 plus positive 1. And so it does. So that's how you do that one. Any questions on that one? No, everybody's good? All right. So what was the other one that you were asking about? It was something with xenon. Anybody remember? XeO3? Okay. All right, so with XeO3, we are going to do the same thing. We're going to start by counting the valence electrons. And this one's going to seem a little weird because xenon is a noble gas and it normally doesn't bond with anything else. But we're going to, occasionally they can be forced to bond with other things. So xenon, how many valence electrons does xenon have? 8, because it's a noble gas. And oxygen has how many valence electrons? 6. How do we know how many valence electrons something has? The family it's in, the group that it's in, on the periodic table? Correct. So we're going to go with the AB numbering system. And so that goes 1 through 8. And so whatever group it's in, it's the same number of valence electrons. All right, so we have 3 of the oxygen, so that's 18 plus 8. So that would be the same as 20 plus 6, 26. All right, so now we're going to put them all together. Now, xenon is not electronegative because it's a noble gas. So when you do the little trend where electronegativity gets bigger as we go to the right, it kind of stops at fluorine. And then we have the noble gases. And technically they will have some electronegativity, I guess, but for the most part, they're just satisfied. They have an octet, so they're going to be less electronegative than oxygen. So we're going to put xenon in the middle. We're going to put oxygen here. So that's going to be minus 6, leaving us 20. What do we do with these 20? Yeah, we're going to put them on the oxygen. So you always, once you've made your skeletal structure, you're always going to fill up the outside atoms and then go back and check on the one in the middle. Okay, so that's 18. Oh, you're quicker than I am. Yeah, I hadn't even got to that question yet, but that's exactly what I was going to ask next. So when we calculate this, we notice we've got 2 left over. So just like Lexi said, those 2 leftovers go in the middle. All right. So now we're going to check and see if xenon has an octet in this structure. Does xenon have an octet? Yes. Oh, Kevin, you have a question.
Yeah, I was just going to ask, what do you mean by the 2 that go up over xenon? What are those 2 coming from?
This is just a lone pair. So when we counted out all the valence electrons we had to start with. So we had 26. Then we connected them together, so that used 6, and that left us with 20. Then we filled up all the oxygen, and then that was only 18. So we had 2 leftovers. And anytime you have leftovers, they always go on the middle atom. So it's just a lone pair in the middle.
Okay, thank you.
You're welcome. All right, so now let's check the formal charge. How many valence electrons does xenon have? It's a noble gas. 8, correct. So 8 minus dot, dot, dash, dash, dash. So that's 1, 2, 3, 4, 5. All right. So then what about the oxygens?
I thought that the lines were 2.
They are, but when you're doing formal charge, that's a good question. So when you're doing formal charge, so that's the valence electrons minus the lone pair electrons plus the bonds. So in the case of xenon, we have 8 minus the 2 lone pair electrons plus the 3 bonds, and that equals plus 3. Correct, yes. So we're just kind of splitting the bond and saying, okay, each line is 2 electrons, but since we're trying to calculate formal charge, which is sort of an imaginary thing, we're kind of breaking it and saying, we're not really breaking a bond, but we're saying, well, one of those electrons belongs to oxygen and one of them belongs to xenon. That's not really true because they share them, but just for this purpose, that's what we do there.
So for the lone pairs, we only count the lone pairs for the middle element?
Well, when we get to doing the formal charges, For the other ones, we'll count the other ones. But in this case, we're just counting the ones that are on xenon because we're doing xenon's formal charge. So yes, when we count the lone pairs for the formal charge, you only count the lone pairs that are on the atom that you're working with.
Okay.
And I should say lone pair electrons as opposed to lone pairs. All right. So that would be +3. That's pretty high, actually. And then oxygen is 6. So we've got 6 minus the 6 lone pair electrons plus the 1 bond. And that's going to be -1. And all of the oxygen are identical. So they're the same there. Now, there are a couple other things. I mean, we could try a couple other structures probably. Let me look at something real quick to see if we even need to bother with that. We could try it with oxygen in the middle and see how that goes. But oxygen is not is not the least electronegative, so it's just not going to go in the middle generally. Xenon is +3 because xenon has 8, so it'll be 8 minus 2 plus 3. That's a good question though, Chad. That's all right. Yeah, oxygen is 6 and xenon is 8. All right. So let's see. Anybody have another example we should try? I'll give you one. Try drawing this. And then calculate the formal charge on the carbon and the nitrogen. So this is the cyanide ion. Oh, I'm not saying anything yet. Oh, so SF3CN. All right. Do that in a minute. Anybody have the structure yet? Iron sulfate, okay. Two little structures for this, okay. Chlorine bond, and the other with chlorine, oxygen chlorine. Yeah, we can do that one, sure. All right, so let's finish this one. So how many valence electrons does carbon have?
4.
4. All right, and how many valence does nitrogen have?
5.
5. And since it's a negative charge, do we add or subtract?
Add 1.
Add. So that's a total of 10 electrons. So the skeletal structure has carbon connected to nitrogen, and we've used 2 electrons. So we have 8 left. So we can either give carbon an octet and then put the other 2 on nitrogen, or give nitrogen an octet and put the other 2 on carbon, or we can give each one of them 4. It doesn't really matter. I'm going to give nitrogen an octet just because, you got to choose something. All right, so I've used 6. I have 2 left, so we'll throw them over here on carbon. All right. Does carbon have an octet?
No. Wait. 6, no.
No. So how do I get carbon to have an octet?
You had to add 2.
Yeah, triple bond. So I'm going to start by taking these and moving them down. So that's going to give me carbon, double bond, nitrogen. But again, still doesn't have an octet, it's just got 6. So we're going to move these. And then our final structure is going to look like this. And then, of course, we remember the brackets like that. And now they both have an octet, and we've used all of the electrons. So we're done with that. So now we've got to calculate the formal charge on carbon. So carbon has 4 valence electrons. So what's its formal charge? Correct, -1. So that will be 4 minus 2 plus 3 equals -1. All right, so nitrogen has 5 valence electrons. So what's its formal charge? 0. So it is 5 minus the 2 electrons here, plus the 3 bonds. So 5 minus 5 equals 0. So what's the charge of the cyanide ion? -1. So if we add the 2 formal charges together, -1 plus 0, we get -1, and that equals the formal charge, or not the formal charge, it equals the charge. So that's good. So why is it 2 plus 3? That's a good question. All right, so looking at nitrogen, it's going to be the 5 valence electrons minus the lone pair electrons. So in nitrogen, it has 2 lone pair electrons. And then either half the electrons in the bonds or just the number of bonds. That'll be the same number, either way you do it. So that's 3. So 5 minus 2 plus 3. Does that make sense to read?
Dot plus bond, and dot plus line.
Okay, so what happens if the formal charge doesn't match the charge of the structure? There could be a couple of things that went wrong. One, you could have assigned the formal charges wrong, so you might want to go back and recheck the charges. The next thing you also want to check is you want to make sure you counted up the valence electrons correctly. A lot of times if it doesn't equal the formal charge, most of the times you just didn't count the valence electrons correctly. But the other thing, I think those are pretty much the only 2 things that are going to do that. You can also rearrange them, but most of the time, even if you rearrange the order of the atoms, then it'll come up with the same total as the charge. So for instance, if we had 3 atoms, we had A, B, C, we could mix them like A, C, B, or whatever. generally, not always, generally, they're going to give you the same number once you sum everything together. They're not going to give you the same formal charges, but they'll give you the same thing. So formal charge always equal to the charge of the structure. Yes, that is correct, Zatura. You're welcome. All right, so let's try that other one somebody had with the chlorine in it. Anybody need a second on this picture? Okay, so SF3CN. All right. All right, so what did they tell you about SF3CN? Oh, nitrogen wouldn't have 6 dots. It would have
Okay.
5
Okay.
at most.
Okay.
So in the question, what did they tell you about SF3CN? Bond links indicated below. Okay. Let's see. Complete the Lewis structure. So I'm guessing they showed you something like this. S, F, 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 C, N. Something like that? Okay. So in these where they give you the structure and then they tell you to complete the Lewis structure, what you have to do is start with the counting valence electrons. All right, so fluorine is in group 7, so there are 7 of them. We have 3 fluorine, and then sulfur's in group 6, and nitrogen's in group 5, and carbon's in group 4. That's going to be 21, and 4 is 25, and 5 is 30, and 6 is 36. Okay, so we're going to go back and count all the dashes, all the lines, to count how many electrons we've used. So each line has 2 electrons in it. So it's 2, 4, 6, 8, 10, leaving 26. So now we're going to do what we did before, which was give everything on the outside an octet.
Oh,
All right,
so they
so we've
make it
used
like that.
18.
Okay.
So that leaves us 8. So 1, 2, 3, 4, 5, 6, 7, 8.
6, 1, 2, 3, 4, 5, 6.
All right, so now we've
1, 2,
used
3,
8.
4, 5, 6.
So looking at this, I can tell that all 3 fluorines have an octet. Sulfur has an octet. Nitrogen has an octet, but carbon does not. Now, carbon could share by taking lone pairs from sulfur if sulfur had lone pairs, but it doesn't. So the only place we can pull electrons from would be from nitrogen. So nitrogen is going to donate 2 electrons here and give you a double bond there.
Mm-hmm.
Yes. So now carbon has an octet. Nitrogen has its octet. Everything has an octet. So at this point, we're good. And this one is a little bit tricky because normally we put the electrons on the outside atoms, but in this case we kind of had 2 outside atoms. But in this case, it wouldn't matter too much. I mean, it matters a little bit where you put the electrons, but the thing that you want to look at, oh good, I'm glad. That's a good thing. The thing you want to look at is the electronegativity. So I believe you have carbon here, and then nitrogen here, and then oxygen, and then fluorine, or something kind of like that. Fluorine is the most electronegative. Carbon is the least. So would nitrogen have more electronegativity or less? Less. So is carbon more likely to have more electrons, or is nitrogen more likely to have more electrons? Those are good guesses. So to be electronegative, what that means is you're going to draw electrons toward you. So carbon is less electronegative. So it's not going to draw electrons toward it as much as nitrogen's going to draw electrons toward it. So if nitrogen is drawing electrons toward it, it's more likely to have more electrons on it. And so that's how I know to put the electrons on nitrogen to start with, to fill its octet up first, because if I fill up carbon's octet first, then I would be putting more electrons on the less electronegative atom. But if I didn't know for sure, what could I do? What would tell me for sure if it was this structure here, or if it was a different structure? So formal charges. All right, so let's, I'll show you kind of how to do that. Major resonance structure. Oh yeah, I don't know why they call them major resonance structures. They're just resonance structures. I guess they're major because in some case, okay, I'll show you why they're major. Hang on just a second. Okay, anybody have any questions on the one we've got up right now? No? Okay. All right, so let's look at this imaginary molecule. We've got A, B, 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 maybe C, like that. All right, and then, or better yet, let's do this instead. A, B, B, C. So when we're doing resonance, we would put a double bond on that is almost equivalent to doing this. Like that. Those would be the two major resonance structures, but there is a slight resonance structure like this. But when they say major, they mean that if I had a bowl of these molecules and they were enormous and I could see them, and there were 100 in my bowl, I might have 48 like this and 48 like that. So percentage. And maybe just 4% would be like this. So when they say major resonance structures, they mean this kind, the kind that most of them would be. And for the most part, I don't think they're going to give you anything odd, like show you that, I don't think they would give you something like this. When you get into organic, you'll see stuff more like that. I think they're saying, they're just getting you used to the term major resonance structure before you get to organic, and they show you more about the resonance structures, and then you find out there could be others, and then it just would seem kind of like, hey, but I thought there were only two. Yes. So in this case, in my And B does not stand for boron here, and C is not carbon, but is just some generic atom. And this imaginary thing, my generic atom that's more electronegative is B, and the less electronegative one would be C. Okay. So what other ones can we do? We got 4 minutes, so we got time for like maybe one more. Cl2O7. Okay. All right. So let's see. There are a bunch of different options that you could start with this. My guess is they probably gave you a starting point. What starting point did they give you? Chlorine-chlorine bond. Okay. Oh, and a chlorine-oxygen-chlorine. Okay, so this was like one option and the other one like that. Okay. Was it 07 with 7 oxygen? Wow, that's a lot of oxygen. Okay. I've never even heard of Cl2O7. All right. So, I guess you could just start throwing some oxygen on here.
Oh, what the hell?
All right, so that's one option. And then the other option would be something like this. Let's see, 3, 4. Oh, I did ClO8. Hang on a minute. Let me try that again. 4, 5, 6. Let's see, 1, 2, 3, 4, 5, 6, 7. That would never happen. Okay, and then the other one, ClO, ClO, O, 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 O. Well, the second one is probably the better structure. But let's take a look at the formal charges. There's a lot of dots to have to put in. I'm going to put in little lines around them just to save time. And each of these little lines is I'm just going to have count as 2. I should be putting in dots. It's just we're almost out of time. So. Okay. Actually, I should have double bond. Okay. So if we were to calculate the charges, the formal charges on these, they would be really weird. We'll start with the one on the left. So oxygen is 6, 5, 4, 3, 2, 1, 0, minus 1. So every oxygen that looks like that is minus 1. And then, oh, because it didn't have an octet yet, so it had 1, 2, 3 bonds, but it would need 4. So it just borrowed 2 electrons from the oxygen to make a double bond. That's a good question. All right. And then, you know what? Let me do something to sort of separate these two from each other. So the chlorine is 7, 6, 5, 4, 3. This one is the same. And then, let's see, is oxygen on top not with it? Which oxygen on top? You can circle it if you want. That one? No, it's with it. It's with it. The line is just kind of too far away. Oh, good point. Yeah, you guys are right. I didn't see that one. Good point. Yeah, okay. I drew the electrons in straight lines instead of dots because I'm in a hurry. They really should be dots. They should not be straight lines like I drew them. Just because I'm in a hurry, I did the straight lines instead. So that was also -1. And then this chlorine here is pretty much just like the other chlorines. So that's +3. This was +3. And then the oxygen here in the middle is oxygen is 6, 5, 4, 3, 2, 1, 0. All right. So if we count up all of these, and then this one right here is going to be 0 as well. I'm looking at them. And the one on the left has 3 plus 3 plus, let's see, 1, 2, 3, 4, 5, 6. So -6. So the overall thing is 0. And then it's, let's see, 1, 2, 3, 4, 5, 6. And then 3 and 3 is 6, which is also 0. And then the +3s are all on the chlorine no matter what you do. How odd. So what did they want you to do with this structure? Did they want you to determine which one was better? Or just draw them out and find the formal charges? Minimize the formal charges. Oh, to minimize the formal charges, well, I'll have to look at this one to draw both. Okay. Yeah, because they're kind of equally good, technically, because of the formal charges. They're not the same molecule at all. The reason they're not the same molecule is because one has chlorine, chlorine, oxygen, and the other one is chlorine, oxygen, chlorine. And then to kind of, let's see, it's kind of the difference between having H2O versus H2O2. So even though they're really close, they're just not the same thing. So yeah, if all you had to do was draw them, I would draw them like this. I mean, making sure that you don't put in a don't put a double bond there. And then keep in mind that these are all actually dots. You know, not actual lines. So yeah, I guess that's it. All right. So I guess I'll see you guys on Wednesday. Office hours are canceled today. I have somewhere I have to be this afternoon. But I will have office hours on Wednesday, and then we're going to have a review on Thursday night. Oh, that's okay. I can always go back and watch those and tell that, you know, when things are really weird or when the computer's just acting strange. I can really only do one on that day, but I can record it for you if that would help. Would that help?
Yes, yes. That will help me a lot. Well, I don't have any glasses.
Okay, good. I will record it.